Okay, so we're on part 2 of the Unit 6 take-home test, and I'm going to pick up with our naming. So let's review how to name our formulas. We started this in the last one, we're going to finish it up. So 4-step formula for anything that is ionic. So if you see an ionic, if you see a metal in the first element, you know it's ionic and you need to use your 4-step formula rules. Step 1, we're going to write our symbols. The symbol for lead is Pb. The symbol for sulfide is just S. Step 2, we're going to write our charges. I know the charge on the transition metal because that's what the Roman numerals job is. Okay, so if you see a 4, it's there because the oxidation number is a +4. We know sulfur is always the same thing because it is in the group 16. They always have a -2 charge. And if we have ionic, the next thing we have to do is our step 3, which is crisscross. You have to crisscross. So the 2 is going to come down, the 4 is going to come down, and our last step in our 4-step formula is to reduce and erase. If you can reduce it, you must reduce it. In this one, I can and I must in order to get the right answer, because almost right is wrong. So I'm going to reduce that down, and my final answer should be PbS2. Alright, so let's practice another one of those 4-step formulas in the next problem. So it says iron 3 oxide. Step 1, symbols. Step 2, charges. I see a 3 there, so I know I must put a +3. Oxygen is always -2. And then I'm going to crisscross. So the 2 is going to come down here. The 3 is going to go over there. My final step is to reduce and erase. I can't reduce this without making a fraction, so I'm going to leave it alone. Alright, how about covalent things? Let's look at this one. These are so much easier. If you see a prefix in there, for sure, you should not be giving it any kinds of crisscross. What you see is what you get. With your covalent, they don't change. What you see is what you get. So you have to do a quick little prefix review. Tri is 3. So I'm going to write my N. I'm going to put a 3 underneath it because it's nitrogen. And it says deca. Deca is 10, like a decade. Decade's 10 years. So deca chloride. So Cl with a 10. So another quick little review. Let's look at some of these other ones because they review a few other prefixes that we don't use as often. Penta. What does penta mean? That is 5. So pentasulfur. So S with a 5. Oxygen right there. Now normally the prefix on this one is tetra, but when we put it with oxygen, A and O together in English don't really make a sound, so we just drop the A. But tetra means 4. Alright, and one more covalent name because I want to make sure we all understand one of the exceptions with covalent naming. Covalent naming is normally quite easy, but we have one little exception. If you have only one in the first part of the name, we just don't put mono. So we would not say monocarbon, monofluoride. So that's just one little exception to keep in mind. So there are only one of each of these, and I'm going to write it like that. Okay, if you draw on your little happy face, that is very crooked, you get a +1. Oh, and another little bonus, +2, because we reviewed most of the other prefixes, but we did not review all of them. So I'll put it in one place if you write these down. Mono, 1, di, 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta, which is one of the weirder ones, that's a weird looking P, hepta is 7, octa 8, nona is 9, and deca is 10. So get another +2 if you write those down. Okay, so moving on. Now we're going to go to the next problem, empirical versus molecular. This says which formula is most likely to be the molecular formula of a compound with the empirical formula C3H4. I like these kind of problems because it's almost like being a detective and working backwards. So if we're looking for a molecular formula, that means we want an unreduced formula. So I have to think about, I want to multiply these by the same number, and if they can reduce down and it will match, then I've picked the correct one. So I think the easiest way to do these is to reduce the ones where you can. So I'm going to look at choice A. I can't reduce this, and these don't match. Okay, there's nothing I can do to, if you know, imaginary 1 there, because we don't usually write out the ones. These are not the same formula, so that one's out. Can't be that. These are also not reducible and not the same formula. That's out. Once again, if I reduce this, it would be just CH. That's not the same formula. Last one I'm going to try. I'm going to reduce this by dividing by 3. I'm going to reduce that by dividing by 3 again. And look, they match. So choice D is correct, because if you reduce that, they're going to match. All right, next part. And okay, and continuing on, we're just going to keep looking. We're going to go step by step and look for the ones that are not able to be reduced. So if we cannot reduce it, we will be circling. I'm going to look at this one right here, this MgCl2. MgCl2. Understood 1, if there's nothing written there, I cannot reduce that any further. So this would be an excellent example of an empirical formula. Okay, so how about this one? They both have a subscript of 3. So even if the subscript is the same thing, I can still reduce it. I could divide both of those by 3. So this is actually a molecular formula. So nope, we don't want to circle that. Let's look at this one. Now, even if you can reduce, if it's one with 3, like this compound here, it has 3 subscripts, and you can reduce these 2, but you cannot reduce the 3, okay? So I can't say, well, maybe it is because I could reduce these down to NaS. No, we can't do that. This is still an empirical formula. You have to be able to reduce the entire compound by the same number. So this one is empirical. Here's an example of a 3-element compound that is reducible. All of these I can reduce by 6. So 6 divided by 6 is 1. 12 divided by 6 is 2. And 6 divided by 6 is 1 again. So that one is an example of a molecular formula with 3 elements. Okay, so I'll let you finish up the last 1, 2, 3 of those so we can get to the rest of the review. So this As the molecular formula of the compound is X6Y3. What is the empirical formula? So again, we want to think about empirical means we need to simplify. Reduce it, reduce it, reduce it. I can reduce both of these by the same number, 3. Okay, so X, 6 divided by 3 is 2. 3 divided by 3 is 1, and remember, in chemistry, you don't see subscript of 1 written, so I want to find the one that matches. There it is. It's understood to be there, but you don't have to write it. All we did was divide by 3. Okay, so number 34 is a little bit different. And we did an example like this before. It says if it has the empirical formula PO4, what would likely be a molecular formula? So just like we did on a problem similar to this on the other page, we want to look at your options, reduce them if they can be reduced. This one I cannot reduce, and it matches. However, these are the exact same numbers, so this is probably not a really good example of a molecular formula because they're the exact same thing. Choice B, they're turned around, and this one is an empirical formula. They don't match. That's not a good choice. Choice C, if I reduce it, it would be P1, which I'm not going to write, O2. That is not the same. So let's look at my last choice, choice D. All right, I'm going to reduce that. 2 divided by 2 is 1. Okay, so just the P. 8 divided by 2 is 4. So this one, if you multiply these by 2, this is a good choice. A is not a good choice because A is also an empirical formula, and it's asking you for a molecular formula. Okay, so we want to think about what could we multiply it by, what coefficient to make it more true to the definition. So choice D. Okay, number 35, we're going to do scientific notation. This is a really, really large number. So it should have a positive exponent. Anytime you have a number that is larger than 1, greater than 1, your exponent is going to be positive. So right away, take out the garbage. That's a bad choice because it's a negative exponent. So from there, the other rule you have to remember is that there should never be more than 1 digit in the front. Okay, so choice A, what do I mean by front? I mean to the left of the decimal. In scientific notation, you only want 1 digit in front of the decimal. Choice A, there are 2 digits in front of the decimal. So that is also out. And choice D also violates that rule. There are 3 digits, and there should only be 1. You should never have more than 1 digit in front of a decimal. And just to review how we even do this, if there's no decimal at all, just plop one on at the end, and then start to count. And you want to count over until you can get it moved over until there's only 1 digit in front. So you want to count and see how many times you had to move. I had to move 1, 2, 3, 4, 5, 6, 7, 8 times to make this correct. So that is choice C. So remember, you always want to take out the garbage because honestly, you didn't even have to count on there. We didn't even have to really do that counting because we could eliminate all the garbage answers. So +1, take out the garbage. Take out the garbage. Okay, and I'm going to do problem 36. Write in standard notation. So now we want to move the other way. So if it's given to you in scientific notation, how are you going to move? Okay, first thing you want to notice, this is a negative number. That means we are going to be moving our decimal to the left because it is negative. So we're going to end up with a number that is small. This number is much, in the example above, this was much greater than 1. This one's going to be less than 1. So plop your decimal down, and I'm going to move it. I like to write these out kind of like this. If I know I'm going to move to the left, give yourself a little more room. So I'm going to move it 1, 2, 3, 4 times. 5 times actually. 1, 2, 3, 4, 5. Because I have to follow what it says. But you'll end up with 4 zeros. So when you're moving to the left, it's going to be 1 less than what the exponent says. So what do I mean by the amount of zeros is going to be 1 less than the exponent? So there's always going to be 1 less zero than what what the exponent says. So my exponent here is -5, so I should have 4 zeros in front because I have to account for the fact that just moving it this way takes up one of those spots. Okay, so let's do one more of these. I'm going to write it in scientific notation. Again, don't be overwhelmed if you feel like, oh, I don't know where to even start because there's no decimal point. Just put one down at the end and then start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9. I only want 1 digit in the front of the decimal, and I had to move it 9 times to get there. Okay. So, one more of these. -3, so I know I'm going to need two zeros in the front because it's always 1 less than when it's a negative number. So there should only be 2 zeros in the front, and you can count it out if you prefer that way. So I can say 1.35, I'm going to count 1, 2, 3 places. So, like I said, when you're moving to the left, when it's a negative exponent, the amount of zeros is going to be 1 less than the number up there. So I have 2 zeros in the front, which is the same as choice B. Okay, and then we're going to finish off. We've done a lot of these, so I'm going to let you do 40 by yourself, but I'll go ahead and work 39 with you, and then we're going to end this video. What is the empirical formula of a compound if the molecular formula is N6O8? All we need to do is reduce. We need to find our common denominator. In this case, it's going to be 2. We're going to divide them both by 2. So 6 divided by 2 is 3, so it's going to be N3. 8 divided by 2 is 4. O4. Okay, so I'm going to let you finish that one off yourself. And happy studying.